Hello everyone, welcome to GenScript for 2016 webinar series. The webinar we are going to present today is Objective and Quantitative Evaluation of Anti-Fibrotic Agents in Animal Models. My name is Andrew Luan, Marketing Liaison from GenScript Discovery Biology Unit. At GenScript, we provide a one-stop solution for drug discovery, including therapeutic antibody generation and optimization, in vitro and in vivo pharmacology testing of drug candidates. It is my great pleasure to introduce our speaker today, Dr. Boza Xue, Senior Scientist from Pharmacology Department at GenScript Discovery Biology. Dr. Xue is a biomedical scientist with over 7 years research experience in the field of oncology, with 5 peer-reviewed publications in top-tier journals such as Science, Blood, and many more. Before joining GenScript, Dr. Xue conducted her graduate research and received her PhD degree at the University of Massachusetts Medical School. Dr. Xue has been involved in developing of the fibrosis model services at GenScript for over 2 years. We will have a short Q&A session after Dr. Xue's presentation. During the presentation, please type your questions in the question box on your panel. Dr. Xue will address the questions during the Q&A session. All attendees are in listening-only mode. Without further ado, Dr. Xue.
Hi. Thanks, Andrew, for your introduction. Hello, everyone. In this webinar, I will describe a revolutionary technology in imaging and quantifying the fibrosis disease production. I will also share you with some validation data we generated using this technology in our fibrosis animal models. First, I will generally mention some background of fibrosis and what kind of technology is demanded in this field. Fibrosis diseases are excessive scar tissue formation in organs during chronic injury and inflammation, which progressively leads to impair or loss of organ function. Fibrosis is associated with wound healing response, and they happen in lung, kidney, liver, and other organs. Although fibrosis accounts for around 55% of deaths in the developed world, very limited therapeutics exist, in contrast to the huge unmet clinic demand. Since fibrosis presents an abnormal increase in an extracellular matrix, including collagen, quantitative characterization of fibrillary collagen in intact tissue becomes essential for both fibrosis studies and clinical applications. Till today, tissue biopsy for the histologic analysis remains the gold standard in tracking fibrosis progression. However, the conventional histologic methods have several limitations. First, it requires tissue staining to reveal collagen deposition, such as Sears red or Mason's trichromosome staining, which itself alters tissue structures. Variation between different staining methods may also affect the results. Second, the sensitivity of the conventional histological staining cannot reveal subtle changes in the distribution and amount of collagen. Last but not least, the staining method and related quantification or scoring by pathologists are more quantitative than quantitative. The scoring system is not standardized. The results are highly subjected to interpretations by the observers. It is not hard to imagine the intra and inter-observer discrepancy is as high as 35% in the assessment of liver fibrosis, despite efforts to improve diagnostic accuracy for quantitative scoring systems. Therefore, a revolutionary technology to objectively quantify fibrosis progression is expected to overcome those limitations in conventional histologic methods. Driven by the telecommunication boost in 1990s, developments in both mode-locked lasers, and highly sensitive optical sensors have made nonlinear optical microscopy, such as two-photon excitation, TPE for short, an affordable option for tissue imaging. Around 2006, second harmonic generation, SHG for short, microscopy was used to measure neurons and collagen with special structural properties, being a non-absorption process that causes no photon chemical damage to specimens. SHG is ideal for tissue imaging. In 2008, those two technologies, TPE and SHG, were combined in detecting liver fibrosis progression. Parameters were systemically optimized, and fully automated quantification algorithms were developed to assess liver fibrosis progression and cell necrosis. Now, GenScript uses these technologies and related automated algorithms for assessing antifibrotic efficacy of reference drugs in our fibrosis animal models. This presentation will mainly focus on the validation data and interpretation of the SHG imaging results. Before we go into the data, I will generally describe the principle of this new technology. The SHG imaging uses conventional non-stent tissue sections that won't generate any photon chemical damage to the specimens. As shown in the schematic illustration of the optical configuration, excitation laser was a turnable mode-locked laser 710 to 990 nanometer with an acousto-optical modulators for power control. The laser went through a DM 490 nanometer, an objective length, and a rich tissue specimen. An SHG signal was connected on the opposite side of the laser source by a high N8 condenser through a field diaphragm and a 450 nanometer bandpass filter before being recorded by a PMT. TPE was collected by the objective lens, filtered by a 700 nanometer short pass filter before being recorded by another PMT. As shown in the above diagrams, TPE measures autofluorescence from cellular endogenous molecules, and it can be tuned to be sensitive to cell metabolism, cell damage, and cell structure. SHG measures highly ordered structures without central symmetry and can be tuned to be specific and fully quantitative to collagen 1 and 3. The imaging could use either 5-micron FFP sections or fluorescence sections without any staining. The two images can be co-localized and analyzed by automatic algorithms. This remarkable technology presents valuable features such as stain-free and quantitative, high resolution, non-destructive, and fully digital. The validated machine learning imaging analysis includes basic and advanced analysis. The basic analysis will analyze the collagen content in the whole tissue section. The advanced analysis will also tell you the collagen fiber complexity by quantifying the collagen aggregation and reticulation nodes. It can also perform regional segmentation analysis. For example, liver tissues could be divided into portal, septal, and perisinusoidal regions. Lung tissues could be divided into parenchymal, lesional, and structural areas. To better understand the following validation data using SHG imaging, a general introduction to our current fibrotic disease model platform seems necessary. Several animal models covering liver, kidney, and lung fibrosis have been established or in development in GenScript. Carbon tetrachloride induced liver fibrosis in mice, as the classic fibrosis animal model, has been validated with pirfenidone in GenScript and has received continuous service requests. Biodiet ligation-induced liver fibrosis models in rats and mice are also available. TAA-induced liver fibrosis and high-fat diet plus LPS-induced NASH models are currently in development, with an expected launch time around the first half of 2017. Unilateral urethral obstruction is used to establish the kidney fibrosis in rats and mice. Imatinib and pirfenidone have been shown with anti-fibrotic effect in the rat model. Intratracheal instillation of bleomycin is used to establish the pulmonary fibrosis model. Nintedanib and pirfenidone, as the only two FDA-approved drugs, have been shown to ameliorate the disease in this animal model. We are also developing the systemic sclerosis model using pump infusion of bleomycin. This model will be available in the first quarter of 2017. In the rest time of this webinar, we will pick 3 representative case studies using the fibrotic disease models to elucidate the SHG imaging results. The first one we pick is CCL4-induced liver fibrosis mouse model. We did a parallel study to compare the SHG imaging with conventional histological methods. This slide shows the schedule of the animal study. 3 groups were used: olive oil as the normal control, CCL4 with vehicle, and CCL4 with pirfenidone. 10 mice were used in each group. Day 14 after olive oil or CCL4 treatment, mice receiving CCL4 were given with either vehicle or 300 mg per kg pirfenidone for another 4 weeks. Then the in-life study was concluded. Animals were sacrificed to collect samples for analysis. As shown in this slide, panel A shows the result of the conventional series rat staining to review collagen deposition. Both the representative images and the quantification by bright field images shows a significant increase of series rat positive staining in CCL4 injected group compared to the olive oil control. Pirfenidone treatment significantly reduced the collagen deposition compared to vehicle treatment. Panel B and C shows a similar pattern. As expected, pirfenidone treatment also reduced the hydroxyproline content in liver tissues. Moreover, expression of TGF-beta-1, the key regulatory cytokine of hepatic fibrosis, was downregulated by pirfenidone at transcriptional level. Panel D shows the increase of ALT and AST levels in serum upon CCL4 treatment, reflecting the liver injury. However, unlike other endpoints, pirfenidone dramatically increased the ALT and AST levels, which likely resulted from the combined hepatotoxic effects of pirfenidone and CCL4. The same batch of unstained FFPE liver tissue sections was used for the SHG imaging. One example of the full image for the slide is shown with green representing the SHG signal and red representing the TPE signal. The SHG signal can be segmented into portal, septal, and perisinusoidal regions by automatic algorithms. Not only the total collagen contact can be quantified for the whole tissue section, the collagen contact in the 3 different regions could be quantified too. Therefore, if any test article only alters the collagen deposition in one region but not another, or with different extent, it could be clearly reviewed and quantified. It is also worth mentioning that the SHG signal in the perisinusoidal region is weaker than other regions, but it is within the detection range of the SHG imaging. In contrast, it cannot be detected by the conventional sears red staining or other histological staining methods. Then we could move on to the pirfenidone efficacy study. Not surprised, a similar effect of pirfenidone on reducing collagen content could be disclosed by the SHG imaging. As I just mentioned, the collagen content in different regions of liver tissues could also be quantified. Pirfenidone reduced collagen content in all the three regions. Besides, the collagen complexity can also be quantified by status of the collagen fiber closing. Pirfenidone affects both the aggregated and the distributed collagen. Reticulation nodes only presented in aggregated collagen but not in distributed collagen. To summarize, the first pilot study using CCL4-induced liver fibrosis mouse model, pirfenidone inhibits hepatic fibrosis induced by CCL4, evidenced by significantly decreased sears red positive staining in liver and stain-free SHG detection of fibrosis. SHG image could distinguish collagen deposition in different histological segmentations, including portal, septal, and perisinusoidal regions of liver tissues. Collagen content in perisinusoidal area can be reviewed by SHG imaging, but not by conventional histological methods. SHG imaging could identify and quantify complexity of collagen fibers. Then we will move to the next model using the SHG imaging technology, that is bleomycin-induced lung fibrosis mouse model. Let's also get familiar with the animal model study design first. On day 0, mice were intratracheal instilled with either saline as control or bleomycin. On day 7, mice who received bleomycin were randomized into 3 groups: vehicle, nintedanib, and pirfenidone. Animals were sacrificed on day 18, and samples were collected. As shown in this slide, pirfenidone as a test dose demonstrated significant inhibition of pulmonary fibrosis induced by intratracheal instillation of bleomycin. This was shown by hydroxyproline content and histological endpoints, including Mason trichrome staining and related Ashcroft score. Nintedanib also showed moderate amelioration of pulmonary fibrosis as a tested dose. Similar as in the previous case study, SHG imaging clearly reviewed the efficacy of nintedanib and pirfenidone in reduction of collagen area. In addition, collagen reticulation, which reflected the complexity of collagen fibers, was also reduced upon nintedanib or pirfenidone treatment compared to vehicle control. Furthermore, SHG imaging can also quantify tissue and alveolar areas thanks to the machine learning imaging analysis. The tissue area increased and the alveolar area decreased in bleomycin group. Nintedanib or pirfenidone treatment ameliorated these changes and to some extent restored the normal lung architecture. SHG imaging could also segment the lung tissues into structural, lesional, and parenchymal areas. The definition of the structural area percentage is the percentage of collagen area occupied by the bronchial tubes, such as bronchus and bronchiolius. To calculate the structure area percentage, the collagen around the boundary of the lumen of bronchial tubes was considered a structural bronchial collagen. It is colored in green in the image below. The definition of the lesion area percentage is the percentage area containing inflammation and interstitial thickening and scarring. To calculate the lesional area, we could utilize autofluorescence images from 2-photon excitation and segment using TPE intensity and tissue texture. It is colored in red in this image below. The definition of the parenchymal area percentage is the percentage area that is not considered a lesional area or structural bronchial area. To calculate the parenchymal area percentage, we could utilize autofluorescence intensity from 2-photon excitation. It is colored in blue in this image below. Using this segmentation, the same images could be colored by different areas. We could see lesional area was significantly increased and parenchymal area was significantly decreased upon bleomycin instillation. Treatment of either nintedanib or pirfenidone significantly ameliorated the changes. No significant difference was observed in the structural area among all the groups. Furthermore, a 2D fibrosis chart could be generated based on collagen content and structure in all groups. In the chart, it is very clear to see that bleomycin increased both collagen content and complexity compared to saline control. The collagen content and complexity reverted towards the saline group upon treatment of either nintedanib or pirfenidone. This chart will be very useful to compare different test articles in treating the same fibrosis model by looking both the collagen content and the collagen structure together. Taken together with SHG imaging and advanced analysis, both nintedanib and pirfenidone were shown to significantly inhibit fibrotic lesion in the lung and restore pulmonary parenchymal region area. This is consistent to the results of the conventional histological staining. The area of tissue versus the area of alveoli could be quantified by SHG imaging. Complexity of collagen could also be quantified by the imaging. Lung tissue section could be separated into various segments, lesional, parenchymal, and structural areas, and quantified individually for collagen contact by SHG imaging. Let's move to the final example, which is the unilateral ureteral obstruction-induced renal interstitial fibrosis rat model. This slide shows the study design. Rats received either sham or UUO surgery on day 0. Then the rats who received UUO surgery were randomized into 2 groups with either vehicle or pirfenidone treatment. 3 weeks after treatment, the animals were sacrificed and the tissue samples were collected for further analysis. Treatment with pirfenidone ameliorates renal interstitial fibrosis induced by UUO surgery. This is shown by hydroxychloride content measurement and also histologic evaluation of connective tissues in kidney using serous red staining and H&E staining. As before, the same batch of unstained FFP sections could be used for SHG and TP imaging, one for measuring collagen and the other for measuring NADPH, NADH. Using machine learning imaging segmentation, the kidney tissues could be segmented into cortex and medulla regions. If you are not quite clear on the calculation of the parameters in the previous case study, we list more details here for your reference. Percentage of the regional area is calculated by dividing the area of the region by total area of tissue. Percentage of the collagen reticulation index is calculated by dividing the number of reticulation nodes by skeleton area. Based on this calculation, collagen area significantly increased in UO group compared to the sham group in total, cortex, and medulla regions. Treatment of pirfenidone significantly ameliorated this increase in all the regions. Similar patterns could be observed in the collagen reticulation index. Then we move on to the similar 2D fibrosis chart. This could also be generated for this case study. The UO surgery increased both collagen contact and collagen capacity compared to the sham surgery, while the pirfenidone treatment ameliorated the change back to the status of the sham surgery. Then, to sum up this UO case study, with SHG imaging and advanced analysis, pirfenidone was shown to significantly inhibit fibrotic lesions in the kidney and restore the renal structure, similar as reviewed by serous red staining. Collagen fiber area and reticulation index that indicate fibrosis complexity could be quantified for total kidney tissue, cortex, and medulla regions by SHG imaging. Now we finished talking about the 3 representative case studies. The advantages of the SHG imaging technology over the conventional histologic analysis are not very difficult to be summarized. First, as the stain-free, non-destructive method, no alteration or damage to tissue structure and integrity will be generated by SHG image. Second, it has a very high sensitivity and accuracy. It can reveal subtle changes in the contact and the structure of collagen and cell morphology. This feature will be very critical in assessing the potential antifibrotic efficacy of a test article. Last but not the least, the automatic imaging analysis algorithms enable to generate objective and reproducible quantification results, avoiding operator-dependent variation that may be caused by the conventional histologic methods. By the way, If you are interested in our fibrosis animal model series, including the SHG imaging, this slide will tell you the general procedure for conducting a customized series in GenScript. An initial discussion between you and our senior scientist will make all of us clear about the study design, timeline, and cost. After signing the contract, we will prepare for the study, which may take around 1 month. Then the in-life study, tissue analysis, and the final report will take around another 2 months. Interim report, once or twice a week, will be generated by our senior scientists during the whole project. Therefore, you have access to the progress of your study and may even change the protocol if any unexpected observation happens. The comprehensive endpoints for fibrosis animal models, including the SHG image, which we are talking about today, the conventional histological staining, including silver thread staining, Mason trichrome staining, and so on, and HE staining. Also, we can also perform IHC staining for specific markers in fibrosis or any marker you are interested to use. We'll also have the basic endpoint for the body weight curve and for the fibrotic organ coefficient, and the biochemistry analysis, including hydroxyproline acids and the serum biochemistry showing kidney function or liver function. And we also can conduct the RT-PCR analysis for specific genes that participate in fibrosis generation, and also specific gene that you are interested in. Okay, that will be what I have for this presentation, and thanks for attending this webinar.
Thanks a lot, Dr. Xue, for the nice presentation. As we mentioned at the beginning, we'll have a short Q&A session after the presentation. Dr. Xue, shall we start to address the questions from the attendees now?
Okay, sure. We have a couple of questions submitted during my presentation. Let me take a look and start. Okay. Let's see. The first question comes as, what is the major advantage of SHG imaging over conventional fluorescence imaging? That is a good question. The SHG exhibits intrinsic advantages over conventional fluorescence image. This is because it is a nonlinear optical process requiring no fluorophore present in tissue. Thus, signals are unaffected by dye concentration or by the photon bleaching. The excitation source can be at infrared range, resulting in less scattering in tissues than in the visible wavelength range, and deeper tissue penetration for imaging purposes. Hope this answers your question. And the next one is, besides liver, lung, and kidney, what we talk about today, can SHG imaging be applied to other fibrotic organs? Sure, it can. So for example, we have validated the SHG imaging in human fibrotic heart tissues. We just need to optimize the parameters and algorithms for different tissues. The segmentation and other information may be different for different tissue. We can evaluate it case by case. So the next question we have is, how much will it cost for an efficacy study in the fibrosis animal model with SHG imaging? Okay, usually every animal study is customized for each client's need. The cost of an efficacy study actually depends on the model, the dosing method, the endpoints, the number of mice per group, and some other information. So SHG image is usually more expensive than the conventional staining method, as you can imagine. But we are trying our best to offer very competitive pricing. Also, a volume-based discount can be applied. Just feel free to contact us by phone or by email. Our technical account managers and our senior scientists will be more than happy to help you in the study design, the cost estimation, and the timeline estimation. Hope this answers your question. And the fourth one we have is, what size for region of interest area do you usually scan in the SHG imaging? Okay, so the typical size for region of interest area is 9 millimeters square, typically 3 millimeter times 3 millimeter. We can also do 24 millimeters square, which is typically 4 millimeter times 6 millimeter. The cost will be calculated based on the number of tissues and the number of regions of interest. We can also analyze multiple regions of interest per tissue if you need. And customized size is available upon request, such as the several regions of interest for a specific area, or you want to do a full tissue imaging. And the next question is, if I choose the SHG image besides the analysis, could I get the original images? Okay, the answer will be sure you can, because we will upload it into a professional website called Wiki for viewing and analyzing the images. You could download them using the account, password, and link we sent to you. Using that web-based tool, you could zoom in and zoom out the image, export the whole image or specific area of the image in different formats, and so on. We could also help on selecting representative images for your presentations. The next question is, how should I prepare the tissue sections for SHG imaging? Okay, so as I mentioned in the webinar, non-stand 5-micron paraffin embed tissue sections or frozen sections could be used for the SHG image. If you are working with GenScript for the whole project, starting from the animal models till the SHG imaging, you don't need to worry about the processing of the sections, because we will take care of processing them for you. And if you are submitting your own tissue slides for the imaging, we will send you a detailed protocol for preparing the tissue sections. Generally, the preferred method is the paraffin embed tissue sections, using the conventional pathology method for tissue fixation and paraffin infiltration. It is possible and sometimes welcome for mid-throughput studies to position several tissues on one slide. And the next one is, how many samples per group I recommend for SHG imaging? So GenScript recommend at least 10 mice per group for most of the fibrosis animal models to have the statistic power for the data analysis. If you have already chosen the histological endpoint, such as serum thread staining or Mason trichrome staining for all the mouse samples within the group, we recommend you to select 4 to 6 samples per group for the SHG image if you are limited in your budget. But if there's no limitation, you could select all the samples for the image, SHG image, and get much more information than the conventional histological method analysis. Okay, we still have a few more questions. So the next one is, how robust and consistent are your fibrosis animal models. Okay, so all our fibrosis animal models have been repeatedly, constantly in our internal research project and in our customers' orders. The degree of disease progression and efficacy of reference drugs may vary within a certain range based on different endpoints. Usually, the histological endpoints, which are more important, are also more consistent than the blood biochemistry results between different batches of the experiments. The statistically significant difference in all the endpoints between like the normal and the model groups, as well as between the model and the reference drug groups, this can always be observed. And okay, we have the next one is how is the SHG imaging accepted by the scientific community? Although this technology needs to be more widely accepted by the whole community, many pioneers in the field are already utilizing it for research and drug discovery, such as BMS, Gilead, Pfizer, Merck, Belgium, and some other research institutes. As far as I know, intravital in SHG imaging of fibrosis is also being developed. With the advantages over conventional approach, I believe SHG imaging will be utilized by more and more pharmaceutical companies, research institutes, and clinics. Okay, the next question is, how much additional time does it take to conduct the imaging and analysis after an in vivo study? Usually, the in vivo study will take around like 5 to 8 weeks, depending on the type of animal models you want to use. And the typical analysis, including conventional histological analysis and biochemistry analysis after in vivo study, will take around 3 to 5 weeks, depending on the number of endpoints you plan to have. If you would like to add the SHG imaging on top of all the analysis, usually additional 2 to 4 weeks may be needed, depending on the number of samples you want to select for the imaging, and also if you like to choose a basic analysis or the advanced analysis. Okay. Let me see if we have other questions. Okay, let me just double check if we have other ones. Okay. Is there the option to send the tissue sections for SHG imaging and quantification? Yes, as I mentioned, that is definitely yes, and you don't need to select our animal model service. You can directly send the tissue sections, and we will give you the protocol for processing them. And okay. Do you include in your service the quantification of already imaged samples? Okay. That depending on how you image your samples. If it's similar as what we did, we can try the quantification. Do you perform analysis in other tissues such as mass aorta cross sections? I think it is doable, but I need to double check with our technical support to see if that can be done. And can you share your slides by email after the webinar? Oh, okay. And this attending want to share it with, so it can be shared with students and collaborators. Oh, that's great. Okay, I will double check with our marketing colleague to see if we can share it. I believe it will be on the website, and you can click it anytime you want.
Yeah. Oh yes, Bertha. Dr. Xue, after this presentation, a link with the archived webinar, like the recordings and the slides, will be shared by all webinar attendees afterwards. Just watch out for the email we're going to send to you guys.
Okay, thank Andrew for the clarification. And do you have any scattered muscle fibrosis models? That would be no, not yet, but that will also be an interesting model to establish in the future. And okay, and for the I think that's pretty much all of the questions.
Great. Thanks again for everyone for today's webinar. I hope this webinar is of value add to your fibrosis research project. If you have additional questions that we are unable to address today due to time limitations, or if you would like to know more about GenScript fibrosis models in detail, please feel free to contact us anytime. Like Dr. Xue's contact information is listed on the slide. Have a great day or night, depends on where you are from. Hope to see you again in future GenScript webinars. Thanks, Dr. Xue, and thanks everyone. Bye-bye.
Thank you, Andrew.